This will be the second video for the AP Chapter 5 review questions. We have 3 questions here. Let's take them one at a time. Number 17 says, a 10-gram cube of copper at a temperature of T1 is placed into an insulated cup containing 10 grams of water at a temperature of T2. T1 is higher than T2, which means the copper, which was T1, is hotter than the water, which was T2. Which of the following is true of the system when it has attained thermal equilibrium? So they're saying we're putting the hot piece of copper into the water and allowing them to transfer heat until both of them are the same temperature. And the specific heat of copper, or I'm sorry, until both of them have attained, is 0.385, and the specific heat of water is 4.18 joules. So they're telling us here that the specific heat of copper is quite a bit less than the specific heat of water. In fact, about 10 times less. So the specific heat of water is almost 10 times bigger. This means it takes 10 times more heat to raise the temperature of 1 gram of water by 1 degree Celsius than it does for copper. And we know this because water has a very high heat capacity compared to other substances. And because remember, heat capacity is how much heat it takes, how many joules it takes to raise the temperature, how many joules to raise 1 gram of water by 1 degree Celsius. It takes 10 times more for water than for copper. And this is true of all metals. Metals have a very low heat capacity compared to water. So which of these is true when the two are placed? So you can say the piece of copper is then put into a beaker of water containing 10 grams. And which is true? A says the temperature of the copper changed more than the temperature of the water. B says the temperature of the water changed more than the temperature of the copper. C says the temperature of the water and the copper changed by the same amount. And D says the relative temperature changes cannot be determined without knowing T1 and T2. So since it takes 10 times more to heat up water than it does copper, the water will increase by a smaller amount. So because all the heat from the copper will be transferred to the water, it takes, so 10 times as much copper can only heat up a tenth as much water. So this is maybe a bit confusing, but the temperature of the water will change much less than the temperature of the copper because it takes so much more heat to raise the temperature of water. So the temperature of water will not have been raised by as much. That's the idea. And the one that matches here is A. The temperature of the copper changed more than the temperature of the water. Because it takes so much more to heat up water, the water would not have heated up by as many degrees. Think about this one. It's a bit strange, but hopefully it makes sense. How about the second one here? According to the data in the table below, we're given a reaction in which we have iodine reacting with chlorine to form iodine trichloride. And according to the table, what is the delta H for the reaction represented above? Now this is a little different than what we've done before. However, we've talked about this concept, and the concept is the average bond energies essentially are the bond, the energy that holds, say, the two iodines together is 149 kilojoules. In order to break this bond, you have to apply or put in 149 kilojoules of energy, which makes sense. And the same thing for the Cl bond and the ICl bond. So what we're doing is we're trying to find out how much energy will we have to use to do this whole reaction. Now, from the reactants to the product side, we see that we have to break an I2 bond, and that would take 149 kilojoules. We have to break 3 Cl2 bonds. That will take this number times 3. And then we're forming 3 ICl bonds, but there are 2 moles of this. So in fact, we are forming 6 ICl bonds. So this will be times 6, is the idea. And we can combine it all together. Now remember that anytime we break a bond, energy must be absorbed. So because we are breaking the I2 bond, we have to do 149. It has to be a positive. we are breaking 3 Cl2 bonds, so the 239 has to be a positive, but there are 3 of them, so we'll have to multiply this number by 3. This is positive again because anytime we break a bond, energy has to be absorbed. And then we said we are forming 6 ICL bonds. That's because we have 3 ICL bonds formed, but we have 2 molecules of it. So we've got 6 of these. This would be negative since we're forming a bond. Heat is released. So negative 208 times 6. So hopefully this makes sense. We're just keeping track of how much energy it takes to break and then to make bonds. So essentially we have 149 plus, in this case, 3 times 239 should give us 717. And negative 208 times 6 should give us negative 1248. And if we total these up, we should get ourselves, if you do this in your calculator, negative 382 kilojoules. And is that one of the answers? Yes, it is. So B here would be the correct answer. So the concept we talked about, breaking, making bonds, can actually be applied mathematically. Let's do this very last one, and this will be number 19. In number 19, another reaction is given to us, and this reaction involves a combustion reaction. So we have a hydrocarbon being reacted with oxygen, forming CO2 and H2O. And these are the type of reactions we've dealt with in Chapter 5. The accompanying delta H is given to us, and it is negative, which makes sense. We are undergoing combustion. A lot of heat should be released. Now what's given to us here are the heats of formation of water and CO2. Remember, these are the energies it takes to form a mole of a compound. And these are what are found in Appendix C of our book. And that is what we've used. Now, the question is actually that's asked backward. It says, what is the standard heat of formation of CH4? So we're trying to get the number from the back of the book for CH4. But we're asked to do it from this reaction. Now, the heat of the total reaction is given to us here. And remember, the heat of the total reaction is actually products minus reactants. So let's go ahead and set this up. We have 2 of the heat of formations. So we can plug 2 of these in. And then we'll have to find the third one. And so to do products minus reactants, we have 1 mole of CO2, and it takes negative 393.3 for CO2. So for our products, we'll do negative 393.3. Remember, we have to total the products. It's the summation of the products minus the summation of the reactants. So we'll have to add our 2 waters. Each water is negative 285.8. We have 2 of them, so we'll do 2 times negative 285.8 kilojoules. And it's products minus the reactants. So let's go ahead and add up our reactants. Now, CH4 is the one we don't know. So CH4 is the one we're going to solve for. And there's only 1 mole of that. And then we have to add the heat of formation of oxygen. Now remember that elements have a heat of formation of 0. So we'll actually put 0 in here for the oxygen, and it'll make it quite simple. So what we've got, essentially, if we multiply this out, if we do 2 times negative 285.8, we get ourselves, this number is 571.6. And so if we subtract, this would be negative 571.6. If we subtract 393.3, we have a total of negative 964.9, which makes sense. It's a big negative number, minus CH4, whatever CH4 is, and this will give us the total, which in this case is negative 889.1 kilojoules. So now it's a matter of rearranging the equation to solve for CH4. So why not we add the, we can add the CH4 this way and then add the 889 this way. I know this is a bit confusing. Essentially, we're just doing a little bit of algebra. So let me rearrange the equation solve for CH4. So CH4, I'm putting CH4 to this side, so CH4 will equal on the right side. And then I've got myself negative 964.9 plus 889.1. So hopefully you see what I've done here. I just rearranged the equation a little bit, added CH4 to the right, and that one to the left. And what do we get for a total? Negative 75. CH4 is negative 75.8 kilojoules. And is that one of the answers? Here it is. So we've done it right. And this is how you would solve a problem. It's really what we've talked about after Hess's law, using heats of formation, just done backwards. So hopefully you've enjoyed these videos and learned from them. Be ready for the test.